Okay, so a little bit on inequalities. Firstly, let's revise number sets. So the letter N represents the natural numbers. What are they? They are positive whole numbers, or full numbers, okay, nothing between. N equals 1, 2, 3, 4, and so on. And on the number line here, you can see the natural numbers marked using discrete dots. Okay, 1, 2, 3, 4. Second group that we come across are the integers, letter Z. They are positive, negative, and 0. Okay, and they are also whole numbers, so no decimals, no fractions, full numbers. There we have Z equals, so it extends into the negative numbers, includes 0, and then goes on forever in the positive numbers. So it is an infinite or never-ending set, same as natural numbers. On the number line, we represent the integers using discrete dots on each of the whole numbers. Real numbers then. Well, real numbers are all numbers, positive and negative, that we can put on a number line. And we represent the real numbers using a solid line. Again, it's infinite, it goes on forever into the negative and positive directions. Okay, real numbers does include fractions and decimals and in between the whole numbers. Okay, so there are the number groups. And then the signs that we're going to come across in inequalities. Well, the word inequality means not equal to, so you don't see the equal sign. We've got greater than points to the right, so the positive side of the number line, less than points to the left, greater than or equal to. Okay, greater than or equal to, you have that extra line on the symbol. And you also have less than or equal to. Okay, so let's do some examples of graphing inequalities on the number line. Okay, so first, if you're told that x is an element of n and x is greater than 3, so what are the possible values of x? So when you're doing inequalities, there can be many different correct answers for x. We get a range of x values. Okay, so we're told x is a natural number and x is bigger than 3. So that means that x can be 4, 5, 6, 7, and so on. And this is how you would represent that on the number line. So discrete dots on the natural numbers that are bigger than 3. So starting at 4 and going to the right. Okay. Now this one is just slightly different. Again, x is a natural number, but this time it says x is greater than or equal to 3. So how does that look different? Well, this time you can include 3 also. So 3, 4, 5, and so on in the positive direction. What about x is an element of z, so the integers, and x is less than or equal to 3. Okay, so first you ask yourself, can we include 3? And the answer this time is yes, because it has the or equal to part. And it's less than, so to the left, and integers can be 0 or negative also. So we start at 3 and go to the left. Integers are whole numbers, so discrete dots. Now, here's one with a real number. X is an element of all. So real numbers greater than or equal to 2. So can we include 2? Yes, we can. So we show that we're beginning at 2 with a solid dot at 2, and then a solid continuous line to the right of 2 for greater than 2. And slightly different, the last one. X is a real number, x is greater than 2. So can x be 2 exactly? This time, no, because we don't have the or equal to bit. So it can't be 2, but it could be 2.00001, so slightly bigger, so just after the 2. And we show that on the line by putting an empty circle on 2 and then a solid line to the right. So it indicates that it's not 2 exactly, but it begins just after 2. Okay. Okay, let's try some linear inequalities. So they're inequalities that have x to the power of 1. And by and large, you just treat them exactly like a regular equation. This one says left is less than right. So if you were to take 3 from both sides, well, left is still less than right. If you were to divide the left by 3, well then, and do the same to the right, left is still less than right. So the same rule applies. If you make a change to the left, you do the same to the right. So solving for x, I'm going to take 3 from both sides. And what remains is 3x less than 9 minus 3, which is 6. We divide both sides by 3, and I get x is less than 2. Okay, now I'm going to represent my answer on a number line. Okay, and at this stage I must take into account the other piece of information that was given in the question. X is a natural number. So natural numbers are whole numbers and they're positive. So I can only use these numbers to the right. And x must be less than 2. So it's not 2 exactly. It must be smaller than 2 and a natural number. So the only possible solution in this case is the number 1. So x equals 1. Okay, so before we go to the next example, we have to make a note of this. Okay, so on the number line, we have x and minus x. Okay, they're direct opposites, and what they're a reflection of each other in 0. Okay, so if minus x is less than minus 2 in this example, plus x is greater than plus 2. Okay, so everything here has changed. So the sign on the x, so minus x changed to plus x, minus 2 has changed to plus 2, but also the inequality sign has changed from less than to greater than. Okay, so minus x and x are reflections of each other in 0. Okay, now what does that mean for us when we're solving? It means at any stage, if you multiply or divide by a negative, okay, which is what happens here if you're switching from minus x to x. Of course, we'll be doing it on both sides. So if you multiply or divide by a negative, less than goes to greater than goes to less than, and the same for the others with the equal sign, so the sign flips. Okay, so that's important. Otherwise, we're just doing equations as normal, except for the occasion when you multiply or divide by a negative, the inequality sign will flip. Okay, so bear that in mind for our next example. Okay, so our next example is here. We've got 4x plus 3 is greater than or equal to 6x minus 4, and yes, our extra information, x is an element of n. Okay, natural numbers. Okay, so what am I going to do here? Solving for x, I will take 3 from both sides, and I will take 6x from both sides. Okay, and what I'm left with is 4x minus 6x, which is minus 2x, is greater than or equal to minus 4 minus 3 is minus 7. Now, here we go. I'm going to divide by a negative number. I'm going to divide by minus 2 on the left and minus 2 on the right. Okay, and so I get positive x, and I get positive 7 over 2, and I've divided by a negative, so my inequality sign switches around. Okay, that's because I was changing from negative x to a positive x, and remember it reflects in 0. Okay, so what is 7 over 2? If it helps, you can change that to 3.5 for your number line. Okay, etc. Okay, so x, we're told, is a natural number, so we'll be sticking to the positive whole numbers. It must be less than or equal to 3.5. 3.5 is here. Can it be equal to 3.5? No, because it's supposed to be natural, and that's not a whole number. So the natural numbers smaller than 3.5 are 3 and 2 and 1. Okay, they're the only possibilities. So x equals 1, 2, or 3. Here we've got an example with fractions, but remember, we'll just treat it as a regular equation until we can't any longer. Okay, so normally we would try and remove the fractions or the denominators by using multiplication. I can do that. My lowest common denominator is 4, so I'm going to multiply the left by 4 and the right by 4. Okay, now we can use division. 4 divided by 2 is 2, and 4 divided by itself is 1. So what remains for my next go? Well, I have 2 times 5x minus 2 on the left, and I just have 1 times, so 8x plus 10 on the right. Okay, let's multiply that bracket. I get 10x minus 4 greater than 8x plus 10. Let's now solve for x. So I'm going to add 4 to both sides, and I'm going to take that 8x from the right. And what do I have left? On the left I have 10x, take 8x, leaves me 2x, greater than 10 plus 4 is 14. So divide left and right by 2, and I get x is greater than 7. And extra piece of information, x is an element of r, so what does it look on the number line? So we're greater than 7, so we're going to the right. 3, 4, 5, 6, 7, 8, 9. Can it be equal to 7 exactly? No, it can't, because we don't have the equal sign. So we represent this using an empty circle and a solid line to the right for greater than. They're my possible values of x. Okay, so this next example looks a little different in that we have 2 inequality signs. Okay, and we see we have x in the middle. What this type does, it gives me a beginning and an end to the range of possible x values. Okay, my approach to these is to take the beginning and the end separately. So I will divide this up into one side has minus 1 less than or equal to 2x plus 4 over 3. So that's one side, one limit, or one end of the range, and the other one I'll take, so you're using the center piece twice. I'll use this part, and I just solve as normal. Okay, so let's work on the left hand side. So I'm going to multiply both sides by 3, and 3 divided by 3 is 1, and so I get minus 3 less than or equal to 2x plus 4. I'm going to take 4 from both sides, and I get left with 2x minus 7. Okay, and solving for x, you would just divide by 2 both sides, and I get x, and here I get minus 7 over 2, or minus 3.5. Okay, now okay, and the other side we do something similar, multiply by 3 again, and 3 divided by 3 is 1, so you get 2x plus 4 is less than 6. Take 4 from both sides. I get 2x less than 0. 4, that should be 4, sorry, that's 2. 2x less than 2. And divide both sides by 2, and I get x is less than 1. Okay, so I have a lower limit for the x. You can read it as minus 7 over 2 is less than or equal to x, or x is greater than or equal to minus 7 over 2. So x will be bigger than this number, and x will be smaller than this number. So let's represent it on a number line. And we can, when the signs point both in the same direction, you can rewrite it as one combined relationship, minus 7 over 2 less than 1. Okay, like so. And when you can write them like that, you can show them on a number line as being one single range. So minus 7 over 2 is minus 3.5. Okay. All right. Now x is an element at the beginning of the real numbers. Okay, so we will be doing a solid line. Can x be minus 3.5 exactly? Yes, it can. So I can do a solid dot there, 3 minus 3.5. Can it be 1 exactly? No, but it could be 0.9999. Okay, so empty circle, and then join together, and that could be x. Okay, any of those values. Okay, so moving on to quadratic inequalities. Firstly, let's remember a little bit about quadratic functions, what they look like on a graph. Okay, so if your quadratic function has a positive coefficient, so something positive, x squared plus bx plus c, you have a U-shaped graph. Okay, and if your quadratic has a negative coefficient, you have a hill shape or an N-shaped graph. Okay, now when we move on to inequalities, the questions are going to ask, when is the function greater than or less than something? So if it's 0, well then it will be your x-axis, and it will be asking, when is the function less than 0? Well then you'll be looking at this section of the graph, and you'll be looking at when x is between these values. Okay, if you're asked when is the function greater than 0, well then you'd have this section here of the graph, and then you'd have two separate sections. So you'd have when x is less than this value, and when x is greater than this value. And what are these values? These are what you need to seek out, and these are the roots. Okay, these are the roots of your equation. So when your equation equals 0, and that's the technique. You find the roots, and then you determine, well, are you working with the range inside the roots or the range either side of the roots? Okay, so that's what we aim to do. Let's do a couple of examples. So here's the first one. Solve a quadratic equation less than or equal to 0. So when is this function less than 0? So firstly, it's plus x squared, so it's a U-shaped graph. Okay, we're going to find where is it 0, where does it cut the x-axis? We have to identify the two roots, and you'll see that it's less than 0 between the two roots. Okay, so we solve it as normal. Solving a quadratic equation, we would simply factorize it, wouldn't we? So x and x, factors of 12, when you add them you can make 7, so it's going to be plus 3 and plus 4. Okay, what we would do to solve then for x, we put each factor equal to 0, and of course we get x equals minus 3. Over here we would get x equals minus 4. So they're my two roots. Okay, you want to sketch your graph. When it crosses 0, you have, this is minus 4 and this is minus 3. You'd have minus 2, minus 1, 0. Okay, when is the function less than 0, so below the x-axis? Well, it's in for the x values between the two roots. It's underneath the x-axis. Okay, so how do we write that? We give our answer as x being between those two roots. Okay, so we write minus 4 as the lesser here. We write minus 3 as the bigger one here. And we look to the question, does it include equal to sign? Yes, well then we can include one in our answer. Okay, and this is my result. The function is less than 0 between these two, when x is between these two values. Okay. Okay, so another example. This time we don't have less than 0. Okay, so how would we solve it? We don't know. Well, we can make it less than, we can make this side 0 here. So just like a regular equation, I'm going to add 16 to both sides, right? And we get minus 3x squared minus 8x plus 16 is less than 0, and this is what we're going to solve. It will give us the same solution as the version above. Okay, now firstly, I don't like working with a leading minus, so I'm going to change the equation. I'm going to multiply left and right by -1. But remember, for inequalities, if you multiply or divide by a negative, so this is changing everything, you also change the direction of the inequality sign. Okay, so that's important in B. If you multiply by a negative, your less than changes to a greater than. Okay, now I'm going to factorize. So 3 is a prime number, so 3x by x, that should have squared. Okay, so we need to use factors of 16. With the 3, when we subtract, we'll get 8. So I'm going to use 3x by 4 gives me 12, and I'll use 4 here, so 12 minus 4 gives me 8. The bigger one has a plus, and that has a minus. Okay, so solve for your x, then put each factor equal to 0. We get 3x equals 4. We get x equals 4 over 3. Okay, sorry, got off the screen there. Alright, and we get x plus 4 equals 0, x equals minus 4. Okay, let's do a quick sketch. It was the one we were solving is this one here, the positive 3x squared. So we base our answer on a positive x squared function, which is u-shape. Okay, we found the roots of it to be, which is the lower one, minus 4 and plus 4 over 3. Okay, 0 is in there someplace. Okay, so when was this function greater than 0? So it is greater before we get to minus 4, it's above the line, and it's greater after 4 over 3, it's above the line. So on the picture, these are two separate areas of the graph, so we have to write them as such. We'll have two separate answers to give. We'll have the function is greater than 0 when x is less than minus 4, so when it's to the left of minus 4. Notice there's no equal to bit in the question, so don't include one in the answer. Okay, and also when x is to the right of 4 over 3 or bigger than 4 over 3. Okay, so I give two answers there. Okay. Okay, lastly we're going to look at rational inequalities. Rational refers to ratios or fractions. So in these ones we see that x appears as part of the denominator. Okay, we're also told x is a real number and that x cannot be equal to -1. Okay, this is just a formality, because if you had -1 plus 1, you'd have 0 as a denominator, and dividing by 0 in maths is absolutely not allowed. You cannot do it. Okay, so we have this information, but it doesn't enter into our calculations. Okay, so dealing with the fraction, normally we would just multiply both sides by x plus 1 to remove the denominator. We cannot do that with inequalities because we do not know the value of x, and because of that we could possibly be multiplying by something that's negative. Okay, if you multiply by something that's negative, we learned that that would change the less than sign to greater than. Okay, so because we don't know, we cannot do that. So what can we do? We can instead do something that will, yes, get rid of the denominator, but also make sure we're multiplying by something positive. So we know that if we square any number, so let's say you had -4, if you square it, -4 by -4, minus by minus gives you +16. So if you square anything, it will always be positive. So that's the logic here. We're going to multiply by something we know for sure is positive. We're going to multiply by x plus 1 squared. X plus 1 squared. So the same to the left and the right. Okay, so on the left, one of those x plus 1's will divide into the denominator, giving 1. And one of them will remain for multiplying at the next stage. Okay, so what's the next stage? We have x plus 1 by 2x plus 4 is less than 3 times. Now I always write this out, okay? Don't go guessing, because often people miss out on the middle terms. So we have multiplies here, multiplies here. You can see that we will end up with a quadratic because we have x times x's. Okay, so multiplying on the left we get 2x squared plus 4x plus 2x plus 4. Okay, on the right we'll leave the 3 for the time being. We have x squared plus x plus 1. So on the left, combining the middle terms, we have 2x squared plus 6x plus 4. On the right, these two would give me 2x. So multiplying the 3, I have 3x squared plus 6x plus 3. Okay. Now, what would be the next thing to do? Well, it would be to gather together everything on the left-hand side, because we have quadratic. Okay, so I'll have 2x squared minus 3x squared. We have, look, 6x and 6x on both sides, so we can take that from both sides. We'll have plus 4 and minus 3, sign there, can you see? And we're left with nothing on the right hand side. Okay, so tidying up a bit, we get minus 1x squared plus 1 is less than 0. Now, what would you like to do here? I'd like to lead with a plus x squared, so multiplying by a negative. What do we do there? We can do it all right. X squared plus x squared minus 1, but change this one around, greater than 0. Okay. Now, so we've got a quadratic. We can factorize it. There's two ways. Let's show you. So firstly, I can see that's the difference of two squares. So I can say it's x minus 1 by x plus 1. Okay, solving each factor equal to 0 gives me roots of x equals plus 1 and x equals minus 1. Or, because there's only the two terms, you could say x squared, solve it, equals to plus 1. So bring that back over there. If x squared is 1, well, there's two possible answers for x. X squared is the square root of 1. X is plus or minus 1, which is the same. Okay, now what were we solving? We were solving this equation. It's a plus x squared equation, which is U-shape. When is it 0? We found it 0 at minus 1 and plus 1. Okay, can you see that? And we're looking for greater than 0. So here and here. Okay, so two separate sections of the graph. So I'll give my answer in two separate sections. I'll say when x is less than minus 1, okay, no equal to bit. So when x is to the left of minus 1 and when x is to the right of plus 1. Okay, and there's my answer.